Hi, my name is Dhruv Venkat, and today myself and my partner, Raif Zaman, will be looking at Project Equip, effective quantum encryption of Internet protocols. Without further ado, let's get started. So before we start the project, let's talk a little bit about us. My name is Dhruv Venkat, and I'm a grade 10 high school student from Sir Winston Churchill High School. Some of my interests include coding, playing video games, and watching movies. Raif is another grade 10 student from Churchill who likes to read, play the guitar, and program as well. With that out of the way, let's get into the introduction of the project, where we'll talk about the project's premise, as well as some of the key principles of quantum computing that you'll need to follow along. So the problem today is that millions of people and corporations around the world experience crippling cyber attacks on an almost daily basis. And these cyber attacks can put important information, such as financial information, at a huge risk. Currently, there are several different innovations and solutions to this problem that have been developed by cybersecurity companies to help mitigate this threat. However, none of these methods tap into a new technology called quantum computing that can completely change the industry as we know it today. Like I said, over 30 million cyber attacks are committed each year against corporations and individuals, and we believe that this problem must be completely mitigated in order to create a safer internet future for all of us. So the big question for this project is, how can QKD be used to mask users' internet protocol addresses to reduce the threat of their sensitive information being stolen by hackers? But why did we choose this project? Well, the purpose of our project is to provide the proof of concept for new and groundbreaking innovations in quantum computing and how it could be used to augment current security protocols, such as protecting a user's IP address, and to do this, we'll be using QKD, or quantum key distribution. So what is quantum key distribution? Well, it's a quantum protocol in which one can generate an entirely random and uncrackable key that can be used for encryption. Note that QKD doesn't encrypt the message or IP address itself. It creates an uncrackable key that defends the message or IP address, and then this is decrypted using a standard encryption protocol, which has already been defined by companies and in different settings. So what's wrong with today's cybersecurity methods? Well, current defenses generally revolve around creating long, highly complex algorithms that are becoming increasingly difficult and long to hack for hackers. However, any key that is created using a traditional supercomputer still will have weaknesses that hackers can exploit in order to obtain illegal data. But however, with QKD, it is literally impossible for a hacker to obtain your key due to the complete randomness of its key generation method. So some of the limits of this project include that the project obviously can't be implemented commercially due to the fact that quantum computers nowadays are not stable or widespread enough to the point where we can create entire global networks that revolve around them. Additionally, we, the testers, did not have access to any industry standard security protocols that we could have used to test our code against, considering that companies keep their encryption and decryption protocols very safe so that none of their information gets leaked out into the public. So the timeline for our project showed that it evolved many different times until it got to the point where we are today. So in late November of 2021, we decided on the project and its scope. And from December 2021 to January 2022, we did a little bit of background research on quantum computing and its applications in cybersecurity. In mid-January, we started to learn about the Qiskit programming library for Python and began to learn small programs with it. In late January of 2022, we began to work on the code for the project, and eventually in mid-February 2022, we completed all the coding and troubleshooting and testing for the project. And then from mid-February 2022 to early March 2022, we spent some time compiling all of our data and findings into this final report. So with that, here's a little bit more background information on quantum computing itself. So what exactly is quantum computing? Well, quantum computing is a field of utilizing quantum properties to increase runtime efficiency and to solve complex problems that have been deemed too impractical or too tough for classical computers to solve. The qubit is the fundamental unit of information in quantum computing, as opposed to the regular bit in normal computing. We can represent quantum states using something called Ket notation, and the steps that states that we are going to worry about for this project are 0 ket, 1 ket, plus ket, and minus ket. And these quantum states can also be visualized on the block sphere, as shown on the right side of the screen. 0 ket and 1 ket, as you can see, lie on the z basis or z axis of the sphere, while plus ket and minus ket lie on the x axis, while plus and minus I are two other. So another thing that we're going to be using in this project are called quantum logic gates. And for this project, we're only going to need two quantum logic gates called the X gate, which is applied along the Z basis of the block sphere, i.e. ket 0 and ket 1, and performs a 180-degree rotation about the x-axis, which thereby switches, for example, 0 ket to 1 ket. The other gates that we're going to be using is the Hadamard or H gate, which is performed along the X basis of the block sphere, and that performs a 90-degree rotation about the y-axis. So, for example, ket 0 becomes plus ket plus, or ket 1 becomes ket minus. So, with that, I'm going to be handing it off to my partner Raif to explain our project approach.
Okay, so now we're going to talk about our project approach and the general timeline and steps that were taken to complete it. So, first, we need to talk about what quantum key or QKD actually is. So, QKD is a cybersecurity protocol that generates a completely random key that can then be used for standard key encryption. It is and the keys it generates are completely unbreakable due to the fact that a hacker cannot use an algorithm on any encrypted data to determine the key as a result of the fact that it is generated completely randomly. And we'll see how this is accomplished later on. So the first step of QKD, it's a process between two people. So let's say it's between me, Raif, and Dhruv. So first, what we need to do is establish an encryption scheme that we can use to conduct this protocol. And only we know what this encryption scheme is. And this encryption scheme is based off of the bases and classical bit states. In this case, we've chosen, if you look on the right, bits 0, 1, and bases z and x. So as long as you have both measurement basis and the quantum state of the qubit, as you can see here, you should be able to determine which classical bit it corresponds to. So if we have ket 0 in basis z, it corresponds to bit 0. So the second step of QKD is that I will generate a random list of classical bits that only I know. So pretend I generate this following list. I would then generate a random list of bases, either x or z, and I would use this basis this list of bases in the next step, where I look at the encryption scheme that we established and encode the classical bits into qubits. Very easy to do, very simple. In step 5, I then send this list of qubits to my friend Dhruv. And an interesting caveat here is that we're free to send this information over a public channel. And we'll talk a little bit more about this later. But once Dhruv receives my qubits, he will then generate his own random list of bases and perform measurements on the qubits himself. So pretend he generates this list of bases. So then when he applies the appropriate measurements for each qubit, he gets this list of qubits. Now, bear in mind that he might have gotten another list that's equally as valid, as because of the inherent randomness of quantum gates and the measurements you can get with them. Sometimes you'll get one state, sometimes you'll get another. They're all completely valid. The point is, whatever states he gets, Dhruv would then look at the encryption scheme and see which basis he used to get each qubit state, and from there he can generate a list of corresponding classical bits. So from using that encryption scheme, he would get the following list: 11001, and that's his list of bits. Then Dhruv and I would compare our list of bits via a private channel, and it's entirely possible that some of the bits that Dhruv measured are different from mine, and that's completely fine. Again, due to the randomness of measurements in quantum systems, that's completely expected. All we have to do is get rid of the bits that don't match, and we're left with our key for that we can then use for our encryption. So why is QKD so unbreakable? Well, the beauty of it is that both parties can actually realize when a hacker is trying to interfere with their data. If you'll remember, I said that I sent my list of qubits to Dhruv via a public channel. That means that if a malicious third party did intercept the signal, they would unintentionally change the data because as you're aware, when you observe quantum states or try to interact with them, you unintentionally change their state. Thus, this would destroy the original data. And then when Dhruv eventually performs his measurements, and then we compare our resulting bit list, we'll find that the amount of bits that match up is not the same. And then that's when we realize that, oh, a hacker has tried to determine the key that we're going to use for the encryption, and we simply have to change channels to a more secure one. Okay, so looking at some of the variables of our project, you can see that our controlled variables were the simulator that we used to run our code, the CHASM simulator, the IDE that we developed everything in, which is the IBM Quantum Experience IDE, and the code that we ran throughout all of our tests did not change in any way. Our manipulated variable is the IP address that we pass into the program, and that's dependent on the user's actual IP address. And the responding variable is the randomly generated key from the QKD protocol. So looking at our code setup, we coded the entire project in the Python language, and all quantum functionalities were taken from the Qiskit Python library, which is a quantum programming library developed by IBM. So taking a look at some of the code that we wrote, here you can see the IP grabber code that obtains the user's local IP, and here you can see the IP that we got. This is a VPN encrypted IP, so not actually a real IP address, obviously. And then that IP is then converted into binary using this for loop and nested if statements. And here you can see the output of that IP address into binary. And then here we have our quantum circuit set up. And here we generate the list of classical bits and the list of pools that we use for encryption in step 1, if you'll remember from when we were talking about QKD from before. So here we have the actual encryption code, which is a very large nested if and elif statement within a for loop, and these all individually apply gates based on the basis. And here you can see the actual output of the code, and you can see that a lot of these have gates attached to them. So, second, this is the code that the second party would use after the qubits had been sent to them. So again, we have a for loop, and it's just a basic NumPy decision if conditional, which lets us randomly apply gates. And then here you can see the output of that. And then here is the measurement that gives us the second party's binary list that you can see right here. And then the key, which after comparing the results and finding and eliminating the bits that don't match, we have our key right here. Do note that for actual commercial purposes, when we need a key of much larger length, we just used only used 20 bits for our project to ensure that runtimes are relatively relatively decent. But this can easily be scaled up in a commercial application. Okay, so this is the actual demo of our code. So here you can see I'm in the IBM Quantum Experience IDE, and here's all our code. This is all in all right here. So I'm going to simply restart the kernel, and the program will run. Uh, to give it a couple seconds. And as you can see, starting to work. All right, and there we go. You can see that it's working. There we go. Here is what circuits have what gates have been applied to all our qubits. Here is the second stage of encryption, and here is the resulting one, and here is our output. So, as you can see, it's pretty efficient. It works perfectly. Yeah, that's the demo. Okay, so getting into the analysis and observation section of our project, you can see that we have a table of compilation times that we gathered after 3 test runs, and we find that the data is quite reasonable and fairly consistent. As you can see, they're roughly around 10 to 11 seconds, and we find that for a quantum application, that is fairly reasonable, considering that quantum technologies are still in the infancy of their development, and there are still quite a few stability issues with quantum computers. So we find that this is quite acceptable. So our general findings found that our code worked perfectly each time, and we were always able to generate a completely random key. Our code is also fairly simple and concise, being less than 100 lines, and that ensures that it is as optimized as possible. As such, this makes it extremely easy to implement on a larger scale due to the relative simplicity of the application, and we believe that when quantum networks eventually become widespread and ubiquitous, for example, small businesses could easily implement such a QKD application into their own cybersecurity, and greatly boost their defenses against malicious hacking. As such, our application is quite easy to expand upon and further develop as quantum technology as a whole progresses.
Hi everyone, it's me Dhruv again, and now I'm going to be going over the conclusion of our project, which consists of reflecting on the overall project, places where we can improve, and further applications of QKD in the real world. So with that, let's talk about some of the sources of error in our project. So the main source of error in our trials conducted was error with the remote connection. Due to the long distance between the testing machines and the actual quantum computers, the connection did fall through during multiple trials. The data for which we did throw out regarding them as outliers. Next time, this error could be mitigated by A, using a more stable internet connection such as Ethernet, or B, using the quantum experience application during non-peak hours to access reduced traffic on IBM's networks. Now, the next steps for this project can be sort of visualized as the funnel method. And the funnel method starts with awareness, which is making people more aware of cybersecurity threats that can be solved with quantum protocols. Then we move on to education, in which we want to educate people on how to implement quantum technology to better their overall lives. Next, accessibility. which consists of finding ways to ensure that quantum networks are available to more people, such as small businesses. Then expansion. Expansion consists of researching other quantum protocols, such as the famous Shor's algorithm that can be used to protect IP addresses or other information. And then practical viability, which consists of working with researchers in the field to implement these protocols in the field. And finally, distribution, which is actually making these encryption protocols available to more people, for example, small businesses, as we mentioned previously. If these steps are taken with the code that we've written and the programs that we've made are elevated such that they can be applied on a global scale, we believe that we can create real global change in terms of cybersecurity. Next, let's talk about some of the specific field applications of QKD. So there are several industries that we believe could benefit from the use of QKD, such as internet cybersecurity, credit cards and banking, which can help protect their users' financial data, protecting government databases so that their information isn't leaked out to the general public, national defense, and etc., etc. There are a plethora of different field applications in which QKD can be used, and I'm sure that you can visualize plenty more. So, finally, let's talk about the general reflection on this project. Overall, we, the testers, believe that this project was a success. Using the tools that we had available to us throughout the duration of this project, we were able to develop a tool that can be used in large-scale applications with very few changes to the actual code or the concepts used themselves. However, to improve this project, we would need to access industry-standard encryption and decryption protocols so we can test our application against attacks that would be expected in the real world, such as, for example, DDoSing or man-in-the-middle attacks. With all of that, thank you so much for watching our presentation, and if you have any questions at all, feel free to follow up with us at our emails. Mine is drewv6@educbe.ca, and Raif's is raifz2@educbe.ca. We'd be happy to take any questions that you might have, and we'll try to get back to you as soon as possible. Once again, thank you for watching our presentation, and have a great day.